All right, so now that we've seen a bunch of reactions that can take place with enolates, let's take a look at how we can actually control what part of a molecule actually is going to react. So for example, let's say that we start off with a compound like this. Okay, and now if we take this ketone, we can react that with aldehyde and maybe follow that up with the addition of methyl bromide. Okay, so what we wind up with then is this product right here. Now what's interesting about this is that it really didn't matter which proton we removed from the ketone. Okay, it could have been removed from the left-hand side or the right-hand side, and we would have basically gotten the same exact product. But what if we didn't have that situation? Let's say we start off with something like this. Okay, so we treat this with LDA and then follow that up with the addition of methyl bromide. Okay, but now we have two very different situations here. Here we have two different hydrogens that could react. Okay, I'll color one of them red and the other one blue so we can keep track of them. Okay, so there are two possible enolates that could be produced. If we were to remove the red proton, this is the enolate that we would make. Okay, or if we were to remove the blue proton, this is the enolate that we would have made. Okay, and if we look at what happens after we add the methyl bromide, okay, we can see that there are two different products that could be formed. Either we wind up putting the methyl group on the more substituted side or on the less. Okay, again, two very different products. And it turns out that only one of these products is going to form. Okay, and the one product that's going to form is going to be this guy on the right hand side. Okay, this is our major product. Almost our sole product, depending upon how careful we are with the way that we run the reaction. Okay, but this is the case for a lot of different reactions of enolates or ketones that have been deprotonated. There are two different enolates that can often form. Okay, and we can distinguish between them as being the kinetic enolate or the thermodynamic enolate. Okay, I want to show you the one on the right hand side is the kinetic enolate that could form. And then the one on the left hand side is our thermodynamic enolate. Okay, and the conditions that produce each enolate are different. So you could relatively selectively get reaction at one carbon over the other, depending upon the reaction conditions that you choose. So if you think about it, okay, so let's break this down into these two different categories. Okay, so we have our thermodynamic and kinetic enolates. Okay, of the two, the thermodynamic enolate is more stable. whereas the kinetic enolate is more quickly formed. So if we look at the two examples that I gave up top here, the thermodynamic enolate was the one that had a double bond that was most substituted. In fact, it was tetrasubstituted. Whereas in the kinetic enolate, the enolate was formed from the reaction of the base with the most readily available proton. Okay, so in other words, there were two possible protons we could have removed on the right side as opposed to only one on the left-hand side. But furthermore, these protons on the right-hand side were much less encumbered sterically. They were easier to reach. Okay, so the reaction happened much more quickly. So any conditions that are going to facilitate the formation of a kinetic enolate are going to be those that allow for those protons to be removed very quickly and very irreversibly. With the case of the thermodynamic enolate, the conditions that are going to favor its formation will be those that allow for the establishment of equilibrium, where the more stable of the two isomers is going to be predominating. Okay, so thermodynamic enolates are going to form when we have higher temperatures. Okay, at higher temperatures, equilibrium is easier to establish. When we have, I don't want to say low, weaker bases, okay, because having a weaker base means that it's possible to do the reverse reaction more easily, and short reaction times. I'm sorry, not short, long reaction times. Enough time to make sure that we do in fact get the more stable enolate. Okay, for kinetic enolates, it's the opposite. Okay, we do not want equilibrium. Okay, we don't want to see any of that thermodynamic enolate being formed. So we want this reaction to be done at very low temperatures. Okay, and we don't want reversibility, so we want a really strong base. Okay, and again, we don't want equilibration, so we want to have very short reaction times. Okay, so let's suppose that we have a cyclohexanone with a methyl group on one side. Okay. If we wanted this to be converted to a molecule that had another methyl group on that same side, so in other words, if we wanted to have it form this product, okay, that would arise from the thermodynamic enolate. We would have to form the enolate with a double bond on the right-hand side. So that means this would have to be performed at higher temperatures. And by higher temperatures doesn't necessarily mean we have to heat it to boiling or anything like that. It could just simply be that it's reacting at room temperature. That could be enough sometimes. Okay, and we're going to want a relatively weak base here. So let's say sodium ethoxide. Let me rewrite that real quick. There we go. Okay, these conditions would definitely promote the formation of the thermodynamic enolate, followed by then the addition of maybe methyl iodide. Whereas if we wanted to make the product that has one methyl group on either side, so that would look like this. In that case, we would want to make sure that we use a very strong base, like LDA. at a very low temperature, and a typical low temperature in organic chemistry is negative 78 degrees Celsius. This is typically chosen because it's fairly easy to attain this temperature in the laboratory. All you have to do is mix dry ice with acetone, and then we follow that up with the addition of the alkyl halide in order to put the methyl group on. Okay, so again, methyl iodide will do that. Okay, so if we're trying to control where the reaction is going to take place, which side of the carbonyl the reaction is going to take place, we can do that by trying to selectively form either the thermodynamic or the kinetic enolates. Now, one last thing to remember about these reactions is that typically reactions that involve the kinetic enolate are more selective. Okay, whereas those involving the thermodynamic enolate is going to be less selective, and the reason for that is that in the thermodynamic enolates, the conditions are going to just simply give you whatever the equilibrium constant dictates. In other words, it's going to be whatever the equilibrium composition is going to be. So if equilibrium dictates that you're going to have, 80% of one enolate and 20% of the other, there's nothing you can really do about that. Whereas with kinetic enolates, because we're kind of being very careful about how much energy we're putting into that system, we can actually get very high selectivities, 90, 99% sometimes. Okay.